That's a color person.
Not as much as you haven't experienced cold weather. The things that it does.
No points for me.
Okay. sorry, guys, but today is the last day in our little deep learning module, and it's so yeah, today's last day in the deep learning module, and we're cramming quite a bit for this, no doubt. And really the idea is to give you guys a flavor of it. And today we're actually getting up to the point where we're using these convolutional neural nets, which is really the bread and butter of most of the advanced neural network architecture. And so we'll go over that, and then you'll apply a couple of these examples to a subset of the iNaturalist species data. So really just a really small subset, but gives you again a flavor, and then there's always tend to learn more by doing and reapplying these patterns. And I just want to point out this is awesome, this video. I didn't know about this guy. 3 blue, 1 brown. Grant something. What's it?
Sanderson.
Grant Sanderson. Thank you. Wow, what a genius, this guy. He made his own Python library, this Manum. Thanks for pointing that out, guys. That was so cool. And then you can actually go onto his GitHub. He's got a repo called videos, and you can see all the scripts that generate these visualizations. So he's a mathematical whiz. It looked like he was working at Khan Academy, Stanford grad. Any other comments about this video or this guy? This wizard?
Yeah, I mean, he just everyone should check out all the videos on his channel. I think he does everything, just starting with linear algebra, all kinds of concepts. Yeah, he's just a cool guy.
Yeah, I was really impressed. I thought it filled in actually some aspects of neurons, and when we talk about these layers and the fact that you have input data and then he has the visualizations, how things get mapped along the way. What is a neuron? It's just a little node, and then you're just figuring out the weights to go to each. And so yeah, I really highly recommend that video. That was a great suggestion. So thanks, Carmen and Peter, for sharing about that. Yeah. Oh, thank you. Wordle. Wordle's the rage. Yeah, cool. Good one. Thanks for that, Ian. Yeah. I think that was a more recent one I saw when I went to the YouTube channel, which is his main jam. Okay. So yeah, this stuff it gets kind of complicated, but there's some basic concepts, and really the coding of it is relatively straightforward considering how complicated it is. And that's again just because we're not feeding it a bunch of rules, we're feeding it an architecture in which the machine learns how to apply rules to then identify things like the number 4 out of this image. So the convolution operation, this is the next trick of the that is really applicable to computer vision, which is convolution. A convolution is really just anything that you apply, like a function that you apply to another function, actually, and you get a third thing back. But if like, let's say, blur this image, you might take a window and then a moving window, and that's a convolution. It's just like averaging its neighbors. So the convolution part is actually, rather than looking at all things at once or looking at one pixel at a time, it's actually the ability to look within a subset of pixels and look at localized properties. So you're applying a window, a stride. We'll get into those terms in a minute, but and then it can define local features. And so this is really how our vision system of a brain works, is that we identify, we might start off with looking at, okay, here's a cat. Well, okay, there's what makes a cat a cat. It's these little features like, oh, the pointy ears and whiskers and eyes, and maybe if it's lucky, a nose that looks like a whale's tail. But really, we are assembling like little features and then mapping that into our sort of feature space and arriving at this higher level concept of a cat. So getting to that point of those features is really where the convolutions help out a lot. So when the network is being built, it's just these little functions that you're adding in to describe additional layers. And these are the two that are most often used together, this convolutional 2D and then this pooling. So it finds local patterns by applying this little convolution. And these are the two features of it that make it just far and away like the most popular thing out there, that wins all these competitions to figure, identifying what's in images, for instance. And translational invariant just means that the cat could be on its side, it could be pitched and skewed, but you can still identify, it could be a different part of the image. The earlier neural nets that you guys did with the MNIST numbers, the number had to be pretty consistent for it to be recognizable. With the convolutional neural net, it can pull out these features. They could be rotated, they could be in different parts of the image, and it still works. So that's the translational invariant part. And then the spatial hierarchies part is that once you get these little individual features, then they could be combined to get at like some higher concept of an ear or an eye, based on like the contours and the lines, etc. So this is kind of the this is a major majorly used feature in deep learning. Unfortunately, we'll get into the unfortunate part, but yeah, so the convolutions are defined by these: the size, the patches, and the depth of the feature. So the size is like 3 by 3 or 5 by 5. That's that neighborhood in which of pixels that it's going to look at to then figure out like what is a feature, or they look at, these will be defined by these things called filters. And then this is kind of what I was saying. You use that little window and apply that filter, that convolution to that neighborhood of pixels, and then you get a different kind of response back. And then those can be used to build up subsequent layers. So the idea is that you start up here and you've got these input features, and then you got these patches that you then run over them, and then you get this output feature map. And there, it's actually a slightly, because of the moving window, you don't have defined features on the outer border of whatever that moving window might be. And you can do some padding. So patches and strides. So this is a 3 by 3 with 2 by 2 strides. So this is saying start this is use the 3x3 window, and start in these different locations on the overall image strides. And then the example that's kind of like the binary example that you guys had before with the movie IMDb classification is the dogs versus cats. So here's a whole bunch of images that you guys will run through this lab, and they're very different. Obviously, there's so much background, there's a lot of angles, there's a lot of things to differentiate in the image to, you know, okay, well, there's a pet alligator, but when it's just a dog versus a cat, then it will find the weights to kind of grab those little features and do a fairly decent job of it. And so also, like before, you guys have you're adding accuracy. So the whole idea of the optimizing engine is to reduce that loss with each epoch as it goes down that stochastic gradient descent. And then as it's reducing the loss, you'd expect it to improve its accuracy. So those are the red lines. And then you're holding out a validation data set because there's this tendency to overfit. So these are data that you didn't actually train the model on, but then you're validating with each epoch. And what that's telling you is that as the validation data set starts to swoop upward, that means that it's starting to overfit. So it's getting very good. It's getting better and better at predicting the training data, but that comes at the cost of not being generalizable enough to apply to a different data set. And that's why we have that separation between the training and the validation. So again, that's separate from the test data set, which isn't even in the mix at all, that we apply at the very end. And in the Kaggle competitions, you know, you're not even, you're given the test data set with no labels, and then usually you're uploading what your predictions are for those test data sets. And so they have truth on the back end, and then that's how you get scored on the leaderboard. Yeah. And then there's all these little tricks to help with making the features that it finds generalizable to other imagery. So you could take your existing image and then apply these little tweaks. There's the image data generator function, and you can play with all these different values, and it'll create different incantations of that original image that will help add another sample to train on, and help it identify in those features in different circumstances. Yeah.
Basically,
yeah, exactly. Yeah, you just make it look weird. You stretch it House of Mirrors style, you know, you're just like pulling it this way and that, moving, changing the location, shifting it so it's at a different part of the image, maybe flipping it, rotating it, the image, and yeah, just applying things so that it becomes more like transformationally invariant, going back translationally invariant, I guess, so that a cat could show up in a different part of the image, and maybe like in a different position or posture, and it still finds those features that it can distinguish. Yeah, so yeah, you guys will be able to do this in the lab. And then there's this other idea of transfer learning. So it can take so long for like really big networks to fit. And you can actually use those existing fitted models on like a new data set, a new problem. And so it will already have some layers that have figured out how to like pull out features in imagery that could be used to identify, for instance, different objects or animals, etc. So this is one that you guys will have in the lab. Similar to getting some of the data sets, the Curious has a little function that you can go and download this pre-fitted model. And I think these are just going to be more and more commonly available. There's a TensorFlow repository for pre-fitted models that you can use. And then it can automatically fit whatever shape goes in, but you can also specify that and include top that's the top, the final classification. And a lot of times you don't want to include that just because you want to apply your own classifiers to your own training data set on top. So an ImageNet is just the name of the way it's applied. So it's got, this is the structure of what they had already fitted. It's a little old, but this actually works pretty well for identifying objects from this ImageNet database. So this is like a really typical thing in the CS world, is that they have these curated data sets, and then they have these regular challenges, and year by year you can see like, how did people do predicting the objects in the image. And it's old because, I mean, it looks like it kind of stopped in 2017. They probably like crushed it and just said, okay, time to have a harder database to predict stuff on. So this is the part where this is pretty cool, actually, because you can take all that that whole model where they used that figured out all these different features and could extract, and then you just add that as another layer. So conv base. So we define conv base here off of that other model, and then here we said, okay, that's the same function we've been using, Curious model sequential. So start there, and then the first layer you can define is some other fitted model, and then I guess you flatten it, and then you can add your own layers. These are the dense, you always add these dense layers at the end to correspond with your data. So in this case, this is the dogs versus cats. So that last layer is just going to have one unit, so it's binary, 1 or 0, and it's sigmoid, so it's kind of clamping it to 1 or 0. So that's great. That's pretty nice. Look at all, I mean, this is 14 million parameters in that base model. So yeah, it's a big one. But it's absolutely intractable on a CPU. I got sort of there with this little lab, but it took over 30 minutes, so it's not really tractable for all y'all. And then I tried the subsequent one, and that looked like it was going to take 30 hours. So yeah, this goes back to just really wanting to get it on a GPU, a graphical processor unit, or even a tensor processing unit. And I think we didn't get it set up this year, but there's actually some grants that we can apply for, and some compute resource, or maybe we could get something like Taylor installed on a server with GPU, but that would be next year. Yeah, and really it's just to give you familiarity with what's possible, and you can try a little bit of this yourselves. And if you also have a GPU setup when you install the TensorFlow and Curious on your own laptops, it might work out and sees that you have a GPU, and take advantage of that. So you could try it in that case. But has anybody noticed that it finds their GPU when installing? Yeah. Okay, cool. I don't think my Mac it has an NVIDIA graphics card. I don't think most Macs do, but you must have an NVIDIA graphics card when we don't. So that's probably okay. So basically, once the chapter gets to this point, it's kind of like, all right, we're not going to try to do stuff that's going to take hours and hours, but at least you guys can read on and get the concepts and so yeah, and you aren't expected to apply anything after this, but this is this part about you don't want the top layers. You want to basically take the convolutional base is just all those layers before you get to the final layers that do the classification to the final trained labels. So it's all those other layers that are building up the features. So that's the base. And then you can take that base and then you can have a new classifier on top of that. So it can take advantage of all those pre-trained layers and then have a new one on top of that. And then you can do this fine tuning where like you keep those layers frozen and then you can then pick a certain number of layers that you allow to get reweighted on top of that. So it's basically taking all that fitting that got applied to maybe a similar problem, like identifying image objects, or maybe it was species, or maybe it was like some satellite imagery, land use, and then you have another specific problem with a new training data set where you can then take advantage of all those existing layers and then just freeze these and then unfreeze these and then do your final classification. And that's transferring the learning from past times. So yeah, this stuff is generally called a black box because it is, I mean, it's pretty opaque to me. But you actually can see what's going on under the hood, which is quite cool. So it just talks about how you can look at these channels and see where they get activated, because you can have an image goes in and then there's weights applied and then you can get an image out with each layer. And so here we see that it's being activated where like around the eyes and the ears and the nose. So it's basically getting these contours of features that it can then use for subsequent layers. And then this is later on, 7th channel, and it looks pretty similar to me. But then you can keep on going and look at these different layers and what they produce. And I guess initially it tends to be more about the image, and then you're building up these features, and then the weights tend to be associated with trying to reach the end desired output labels, so they can become more abstract. But yeah, and this is just the notion that we might draw a bike and we have an idea of what a bike might look like, and there are certain features and different versions of that. And then there's this other aspect of visualizing. So beyond the taking an input and then an output and looking at those channels, you can go back and look at these convnet filters. So these don't look as obvious to me, but the upshot is that you can see what has the highest activation as being the identifiable part of an image. And this later is what gets used to like draw the bounding boxes of different objects and images. So that's basically it on the convolutional neural nets. And you're really only going to be doing the first couple labs or exercises in the book, and then applying those to a really small subset of species images. So in this competition, there's 10,000 species, and that are the most commonly found species. And then we've got a training, validation, and a test data set. And the training data set, so there are a certain number of species that are not as commonly found, so there aren't as many images. And for the lab, and this is also quite big, if you go here, you can see that this Kaggle competition then references this GitHub page, and then this talks about the different categories. So of course they're not going to tell you how many are in the test images, but so it's a lot of images. And then they also are including the geographic distribution, which is kind of interesting, relating them back to the first lab, where maybe that could be like a prior that you use to limit you can have a probability of it being an image if it's also found in similar space. And then these are the actual files, which are kind of monstrous. So the training images, it's a 1/4 terabyte, and then it's like 3/4 terabyte when you actually unzip it. So we don't need all that. Plus there's a variable number of images per species as you go up towards that tail. So we're just using the train mini images, so it's just 42 gigs, just still a lot. And then there's this extra JSON that describes what it is, but it's not, and this is where, but even these files are pretty big. Tells you the latitude, longitude per image. So there are these categories that say what species it is, basically. And then there's another little annotation that links the category to the image. So what you guys are going to do is so you'll just want to go through and try out these first 2 labs that walks through these. And I haven't yet done the Python, but we can figure out what little tweaks might need to happen together. And so this is just introducing the convolutional layers, convolutional neural nets, with adding these 2 layers that have that conv2D. And this is showing you how, compared to that MNIST numbers data set, it just does a lot better. It's much more accurate what it predicts, and it runs very fast. And it's just because it has this extra kind of these convolutions. So it's like 99% accurate compared to the other one, which is, I don't know, 96 or 97. And then this small convnet. So this is training it from scratch, and dogs versus cats. So I downloaded this from the Kaggle. They asked that you download it, but we don't need to all clobber the server with downloads or waste people's time doing that. So this just sets up the validation, the training, and test directories, and then there's cats and dogs underneath that. And then it just copies it over. You guys can't run this part because you don't have write permissions under the courses folder, but you can read from it and rock on with the rest of this. And this is just testing image size. And then this is actually building out this network with those convolutional layers. And then you can see that also summarized. So yeah, and then this is the image data generator. So what's cool about this is that it actually will resize everything to the same size, which is a pretty critical step to to shape these things so that they have the same size and can be fed into the machinery. And then, yeah, you look at the training and validation, make sure you're not overfitting. And then this is the one that doesn't quite fully work. So this is the using the existing, transferring with the existing layers, and we can get up to this point where we're actually able to use this conv base, and I was able to fit the models up to this point, and then as soon as we get into the fine tuning of this thing, that's where it's like it's a no-go. So I had to stop. So too slow. Yeah. So then all of what I just pointed out is linked to, kind of similar to where I had for the lab 4B, I had links to the different, the sort of the sub labs, the exercises. So this should be under, so the way I navigated here, under course schedule, we have the lab for today, computer vision. And then this is the 4C, this is the third one, the lab 4. And then, so I was just clicking through the HTML versions of this 5.1, 5.2, and 5.3. So don't worry about this 5.3. It's there for your, maybe you want to try it if you have a GPU set up on your machine. But it's mostly just these two. And then you can also copy the source of the RMD or IPython notebook and go from there. So these are just two that you'd want to go through just to make sure you can run it and kind of understand it. And then the idea is that you can access the images for iNaturalist here, and so they've been added. So I downloaded this thing and this zip folder, unzipped it, and then there are all these, each species, so 10,000 species, each species has its own folder, and then there's 50 images inside. So the idea is that, okay, you guys can just get a sample of 10 species, and you can use that similar to the MNIST example. There was 10 digits that you're trying to identify from the images. You guys are just going to identify 10 species. And then to play with the binary classification, like the dogs versus cats, you're going to identify 2 species and use that as an example, and then apply those models with this data. And the way this little, I just wanted to figure out a way that you know, you guys could all do something different, but not make it too painful. So the way this works here is that you all have unique usernames when you log into Taylor. So if I just do this on Taylor, so sysinfo is a little function that tells you about your system. And so, and then we can extract the username by indexing that. It's really slow. It's weirdly slow for something so simple. There we go. So that's best. And then this little guy, this is kind of cool. So you can digest, you can, this is creating a hash. You can use a little algorithm that pushes any character, any data in, and then creates a string based on that character, but you can't go kind of backwards. So this just gives me a number, and And this is actually this is pretty much how like blockchain and cryptocurrencies and all that they generate a hash. This is a hash. This happens to just be a numeric hash. So a block is a block of information, and it generates a hash, and that's what chains those blocks of information together is based on its hashes, so that whatever is inside that block of information, if it changes, it would generate a different hash. So it's very hard to go the other way and say like what that information is based on that hash. Anyway, it just creates a unique number, and that is what you guys can use to set a seed. So, and if I do this, set a seed, and then I run this, what's I10? Okay. Notice that if I do this again, and look at this, I get different numbers. But if I'm sure to set the seed directly before running the sample operation, it's actually the same exact numbers. So this is just a convoluted way of making sure that you guys can run your labs and always get the same random, or it's not so random, but the same index, but uniquely based on your username. So it just makes sure that everybody uses different usernames or a different species. So this gives us an index between 1 and 10,000 species. And you can see that here's we list so we listed the directories in this directory. And then if I look at those indices, then these are the species. And then there's images, 50 images in each folder. And then for the 2 species, you can just get the first 2 from there. So this is then what you can use as a multi-class problem here, these guys. And then here, this is a binary classification here. And then you can apply those labs. So your task is to apply these skills with this new data. And we want to build just okay. One is just with the basic neural net, like you guys learned, and you did the example of movie binary classification 3.4. The only thing that is that before you can do that example, you'll need to pre-process the data. So that image generator aspect you want to look at, so you get the same size images, and then you can feed that in. And then with the this dogs versus cat example, you can then actually build out a convolutional neural net. And then with the 10 species that you're trying to predict, that's similar to the multi-class classification from that Newswire example, so I linked to. And then the real trick here is then you can actually do the dogs versus cat. You just have to change a few of the parameters, like that last activation function, and then the little cross entropy. So it talks about it in the text of the book. And then there's also this slide. Let's see. It's the last one, So yeah. So remember, this is where if we have different problem types, you have a different last layer of activation and different loss function. So you just need to be aware of that to then take that dog versus cat and then make it to go from a binary classification to a multi-label classification. Yeah. So that is your challenge, if you so choose to accept it. Yeah. So why don't I let you guys use the rest of the time, unless you have other specific questions. use the rest of the time to start in on this lab. Also, I'd love to get make sure that all your groups are defined, and I'm late getting things graded and back to you guys. But we have Monday off, and I will have at least labs 1 and 2 graded by the time we get back Wednesday, and then I'll have office hours on I guess I won't have it on Monday, but I could be available Slack, and then maybe we set up a time Tuesday still if you guys want to chat, or we could just, I don't know, extend this again, but let's just see how this goes, and then we're gonna come back and we will we'll have fun with some Google Earth Engine stuff. So you guys all have accounts on Google Earth Engine, and that's awesome. Okay, so I guess there some of the non-meds folks, you might want to, I'll send a link out in the Slack just to make sure that you have a Google Earth Engine account. What was your guys' process for that? Was it a quick turnaround time? Yeah, okay, cool. It used to be a while. So yeah, and then yeah, question. Yeah, no, I'm not going to add more questions. I just want you to be able to actually apply the data to the assignment. There might be more tips to help you do it, but it's yeah, I think that the main thing is just I added these caveats to what. Let's see. Pardon, I have to update the menu. So I'm just asking that you also be sure to split your original images. So there's 50 per species, and we want 30 for training, 10 for validation, and 10 for test. So these are like far fewer files than any of the examples you used to date. So the results aren't probably not going to be terribly compelling, but it's okay for a little learning test case. And then you also want to include an accuracy metric and validation and fitting process in the history plot. So that's what all the more recent models have been doing. And then there's also an evaluate function, so that's once you fit the model, then you can evaluate your test data and see how well it does on that. And then ideally you then compare. So for both of these types, so the binary and the multi-class, you did just a basic neural net and a convolutional one. And then the idea is just to compare, evaluate, like how did they do, which did better. Yeah. So yeah, that's all. Cool. All right, I hope you guys have an awesome President's holiday.
Yeah.